Hey everyone, in this example we're going to use historical data from 500 bank customers to develop a prediction model for predicting a customer's account balance. To work through this program, you're going to want to open the balance underscore data dataset in RStudio, and you'll also want to make sure you have the caret, rpart.plot, and forecast packages installed in R. So the very first thing we're going to do is we're going to import the balance underscore data worksheet and label it my data. I've already done that here. We can see in the pane that it is composed of 4 variables: age, sex, income, and balance. Because we're going to be predicting balance, that's our dependent variable. That holds the place for y in the model that we're about to develop here. Next, we want to load all the packages that we're going to need to use to go through this work. So I've got the code nice, tidy, and printed up here to match example 10-7 in the textbook. The code that you're going to need to solve the homework problem is extremely similar. I mean, extremely similar. I mean, make sure that you update the variable names and you load your own data, but very similar. And as we go along, if there are specifications of some of the code that you don't quite recall, and I don't go on in too much detail, check out sections 12.1 and 12.2 in the text, and that'll set you straight. So I'm going to load these 4 packages: caret, rpart.plot, and forecast. And I'm just going to run these lines of code straight from the source pane by clicking the line that I want to run and then clicking the run button. Then once you run a line clicking the run button, the cursor drops down to the next line, so you can actually just kind of keep doing it. So I've added caret and rpart, now rpart.plot, and now forecast. So now we're ready to get going with the actual construction of our model. So the first thing I'm going to do is set the random seed to 1, and this helps us reduce the likelihood of variance or randomness when we generate multiple trials of a problem. There are some scenarios where you would want to set a number greater than 1. We choose 1 just because it makes it easier to compare your work. So the next thing I want to do is partition my data into training and validation data sets. So to do that, after I set the seed, I create an object, myIndex, that is created with the createDataPartition function, and I'm looking at dividing the dependent variable in this model, balance, up into those training and validation sets. So now I've run that. I've now created my index, and we can see that now in the global environment pane. I'm going to hit run again. I've created that training data set now, so it's 352 observations of 4 variables. That's 70% of my data set of 500 observations. I'm going to do the same thing for the validation set, and you may notice that for the validation set, I'm creating a data set and I'm taking the inverse of my index. So instead of 70%, I'm getting 30% of the data set. My data sets are now formed. So now I want to use my training set to estimate my model. And the whole purpose of the training and the validation set is that we use the training set to build the model, and then we use the validation set or the validation data to help us evaluate how good our model is at predicting things that we're interested in. So again, to reduce the variance from successive runs, I'm going to set that C to 1. and we're going to build our default regression tree by using rpart. Just like when you run regressions, you can create the object, but it will not necessarily demonstrate it for you. So I'm going to use summary default underscore tree to actually pull up a visual representation and summary of what the tree looks like. So here in the console, I now have information about my regression tree. And this information may not make a lot of sense, or it may not seem very easily organized in text, but we can use the PRP function to actually visualize the tree. And I'm going to hit run again so that line 21 runs and we actually see our example tree. So here we see a number of different splits. We can interpret some of the things that we see here, so that if a person's income were less than, say, 76,000, and if somebody's income were less than 76,000, we would estimate that they would have an account balance of $3,106. But if their income were less than $48,000, we would anticipate an average account balance of $2,197. On the other hand, if somebody's income is not less than $76,000, we can then drop down to the next split in our tree. And if somebody's income is greater than $76,000 but less than $154,000, and they were less than age 25, we would anticipate that their account balance would be $3,816. But if their income were less than $154,000 but more than $76,000 and they were older than 25, we would anticipate that they would have about $8,826 in their bank account. So what these trees basically do is they give you rules and ways to classify different sets of characteristics within your data set, and that can be really, really handy. So while decision trees and regression trees may not seem very intuitive and maybe a little tricky to master, they can actually be pretty cool and pretty helpful. And I don't think we necessarily look at them as much as we can use to get really insightful information. They can be used to help you estimate an individual's bank balance, but we've also used them for a lot of other applications, looking at employee retention, looking at different outcomes for patients with different stages of cancer diagnoses. Decision trees are actually really remarkably powerful and really, really interesting. And while we don't get too much of a chance to dig into them in depth in this class, take my word for it, they're pretty cool. So this is just the default tree. To find the best tree, one approach is to grow the full tree and then prune it to a simpler tree based on the prediction errors produced by the cross-validation process. So by identifying the value of the complexity parameter, which is usually denoted with the letter CP, associated with the smallest cross-validated prediction error, we can create the minimum error tree. So the first thing we want to do in this scenario is to grow the whole tree using rpart again. So once more, I'll set that seed to 1. And now we're going to use rpart to create the full tree. And because I've created the full tree, I haven't done anything to visualize it. I'm going to use the PRP function now so that we can take a look at it. And it may take a few seconds, and we end up with a very, very, very intense and detailed tree that is, well, maybe not the most useful tree in the world. So we're going to go ahead and find the value of the complexity parameter associated with the smallest cross-validated prediction error using this printCP function to help us try to find the best, simplest result. So here there are the specifications for all of the different possible trees that could be generated in the console here. It illustrates the formula we use to produce the regression tree. So we do have balance as our dependent variable, and we're working with the training set, and our method is ANOVA. So we use ANOVA when we're working with a prediction or regression tree. You'll use class if you're working specifically with the classification tree. So the variables used in the construction of the tree are age, income, and sex. And we had a data set with 352 observations, 70% of our original data set. So here we see that we have our whole list of trees. There's a lot of stuff going on. And we find that the tree with we find that our minimum error tree is this one here. It's our third option that has 2 splits. But if we're looking for our best pruned tree, that would be tree number 2, which has 1 split. So to actually build this tree that we like, our best pruned tree, we will go ahead and use the prune function. And that's here in line 35. Now, for the complexity parameter, to avoid any issues with rounding, and I know issues with rounding comes as an enormous surprise to all of you who have worked on the homework assignments this semester. I think just about everyone's had an issue with rounding and getting an answer marked correct or incorrect at least once. And I think we've caught them all and fixed them all. That we want to make sure that our complexity parameter number is just slightly larger than the one in the table, but a little bit less than for the next largest tree. So in this case, I modified that complexity parameter number to 9.1424 from 9.1414. And now we're going to produce this pruned tree. In line 36 here. Now this tree only has 1 split, and it is very, very straightforward compared to the last tree that you looked at, which was our full presentation. And we can now, with our pruned tree, predict the average balances of the observations and the validation data using the predict function. So we're going to create something called predicted value that's basically going to predict those values using our validation data set. So I've created that predicted value object, and it is going to use predictions from the pruned tree and apply them to the validation set. We can take a look at the performance of the regression tree, comparing the performance measures using the accuracy function. So here we have the ME, RMSE, MAE, MPE, and MAPE, and these are all important fit statistics that you can use to compare different trees against each other, and these are also values that you're probably going to want to have on hand when you complete the homework assignment. Now, say we feel like this is a pretty good, pretty accurate evaluation of the data set, we could then decide we want to go and predict scores for, say, 20 new cases. And for this, you'll want to import the balance underscore score data set and call it my score data. And then we can use the predict function again to make predictions for these new values. I've already imported that data set, so I'm going to go ahead and run this code. If you run into any difficulties running this code, just make sure that you've imported that balance underscore score data and called it my score data. And then here I can see the predicted values for the different elements in my data set, and what we see is that all of the values either take on the value of $3,106 in the bank account or $9,818 in the bank account. And it's doing this based on the rule that if you have less than $76,000 as your income, your estimated balance is $3,106, and if your income is greater than $76,000, it is estimated that the balance in your bank account is $9,818. If we had used a tree that had more splits, the values that would be predicted for our score data would probably be a little more complex. There'd be more than just the two options, the two different outcomes. So I hope that gives you the nudge that you need to get through the regression tree question on your homework assignment. We're almost done. Let's finish strong.